Hey guys, the quiz should be up at 5:30. Can you guys, somebody shout out when you do see it up? Thanks. Thanks, Lloyd. Looks like it's up, guys. Just again, I think I put this on the announcements, but notice in both problems, I sub s is the sum of the digits of your student ID number divided by 10. So the sum of the digits in your student ID number, but this time you have to divide it by 10. Okay, if you don't do that, you might go down the wrong rabbit hole or something. So anyway, just make sure you follow the instructions carefully. Good luck.
Professor? Where do we upload the quiz to?
Just email it back to me. Guys, don't forget to put your name on the file name and also on every page in the quiz. Okay, guys, that's our deadline for the quiz. Why don't you guys take a 5-minute break and we'll start our lecture at 6:05. Okay, guys, let's get started with the lecture. Hopefully we'll finish off this freaking chapter 4 finally, and move on to chapter 5 next week. Okay, so let's see. So going back to our this equation that I'm sure you guys are sick of seeing over and over again. You have this. You're saying the collector current is I sub s times exponential of VBE over VT. Okay. And so we're saying, okay, you have two graphs. If we graph I sub c versus VBE, and then you could have another graph that's I sub c versus VCE. Okay, because you could have a collector voltage and a emitter voltage. We said the VBE, there's an exponential relationship here, which is this guy. And then we're saying, well, there's no dependence on, we don't see VCE anywhere here. So given a constant VBE, if we plot I sub c versus VCE, this is going to be a flat line. And then for each VBE, we'll have a different I sub c. But it's not going to, as long as you stay in, as long as we stay in saturation, say, sorry, as long as you stay in forward active mode, so don't go below a certain value or things will go bad. As long as you're here, we said to first order I sub c isn't going to change. Well, it turns out as a second order effect, it will change, because although, you know, writing this equation like this, it doesn't look like there's any dependence on there is a dependence on VCE hidden here inside this I sub s. Okay, so okay. By the way, one of you guys just emailed me that you divided by the student ID by a different number than 10. So if you did something like that, as long as I see it, it's probably okay. It might, I'm just worried, you know, if it pegged you into a place where your analysis was completely wrong, then, you know, that's, unfortunately, there's not much I can do about that. Sorry. So anyway, sorry for the interruption. Okay. So, okay, so there's something hidden here. So if I write up the same equation here, if I write it out fully, okay, so this I sub s is, let's see, it's AE, which is the area of the junction, Q, which is the charge of an electron, diffusion length, the intrinsic carrier concentration, the number of dopants in the emitter, and the width of the base. Okay, and so if I write this whole complete thing times exponential of VBE, there turns out there is VCE dependence here, and it's actually hidden here in the width of the base, because you know, we said
we're implying that the width of the base is constant always, but it actually shrinks a little with increasing VCE. How's that? So if you actually look at the, so this is our NPN. Remember this junction in forward active is this guy's forward bias. So it's pretty much, that's all set. But the base collector junction here is reverse bias. And when you have a reverse bias junction, it actually has a particular width. It's the, what we called it, the space charge region, where there's the actual depletion region where the carriers are depleted here, around here, where there are no carriers. Now, as you increase this VCE, it increases the voltage across this base collector junction and makes it wider and wider. Okay, so this is at a higher VCE. You see the junction width has increased. Okay, and that basically has the effect, this is the base width. Okay, so this is the region where the electrons get, the electrons from the emitter get dumped here. And they get, as soon as they hit the base, the collector junction, they get swept into the collector and get collected. Okay, so as this junction width increases, this point where they get collected moves closer to the emitter, so you're collecting more and more of these electrons. Okay, so that's what happens. So if you actually plot out when you plot out I sub C versus VCE, it doesn't stay constant, but it goes up slightly with VCE. So it has a slope. Instead of being flat, it has a slope. And this is called the early effect. It doesn't mean anything is earlier than anything else. It's just the name of the guy who came up with the effect. I guess his name was Early. So don't get wrapped around that thinking it's like this is a time related something. It's not, doesn't have anything to do with anything being late or early. It's just the name. And so excuse me guys, sorry. This thing is, okay. So and then the way it looks in a VBE curve is it looks like you're getting a sort of a spread in your curve, okay, of the VBE. And so the way we represent it is instead of just having this V1 as VBE, okay, in this case, V1 is VBE. Normally we had just this guy as our current source. But now we're adding a term, which is the VCE. This is Vx, which is the collector voltage. So Vx is VCE over a voltage VA. And this VA is called the early voltage. And notice that if I make the early voltage infinity, so if I say V sub A is equal to infinity, I'm basically eliminating the early effect. So the smaller the value of the early voltage is, the bigger of an effect it has. As you make it infinity, this denominator is infinite and this value goes to 0, and you just end up with the value without the early voltage. So, for example, during the test, I hadn't said anything about V sub A, and if you'd done the homework, you would have seen V sub A mentioned at some of the later questions. And so Kay asked me about, what V sub A was, and it's just infinity. So you don't need to worry about it when V sub A is infinite. But, typically it just depends on, when you get a bipolar transistor in the spec sheet, you'll see, beta, you see I sub S, and you'll see this early voltage. That'll tell you what it is, what to expect. This is a design related thing. So when you're in the large signal model, it's pretty easy. You just, like I mentioned, you just have VCE over V sub A, 1 plus that. So you're just kind of increasing your collector current. Okay. In the small signal effect, small signal model, it turns out that you're just adding it as an extra resistor to the collector emitter region. Okay. And it ends up being this R sub 0, this extra resistor is V sub A over I sub C here. I'm not gonna derive it, but it's fairly easy derivation because we're just basically taking a derivative of V sub E with respect to I sub C. Okay, so basically you just have to add this to your small signal analysis. So then we'd have to figure out G sub M, which is I sub C over V sub T. R sub pi is beta over G sub M. And now if VA is not infinite, you need an R sub out is equal to VA over I sub C. And we'll see, so these are become small signal parameters. And as you'll see, there's the small signal R sub 0, this output resistance, the transistor's own output resistance, basically ends up setting a limit to the amount of gain that you can get out of a transistor, and also because of, anyway, we'll see it. It's just kind of a little bit counterintuitive, but it does limit your gain. So, okay, so I think at this point we've really, let me see if we have anything else I want to talk about. Yeah, I think that's it on the early effect. I mean, the only thing I could have covered. Let me actually give you guys one example, sort of a typical example to give you guys an idea about these numbers. I think we're a little bit more familiar with G sub M and R sub pi, but let's see what R sub 0 looks like. So this would be example 4.14 from the book. And basically it says we have a transistor that's, has a I sub C of 8 milliamp, a beta of 100, and a V sub A of 15 volts. What are the different small signal models? So, here's the answers. So G sub M is I sub C over VT, or 1 milliamp over 26 millivolts. This ends up being 1 over 26 ohms. R sub pi is beta over G sub M, 100 over 1 over 26 ohms, or 2600 ohms. and R sub out is V sub A over I sub C, and that's 15 volts over 1 milliamp, and that ends up being 15 kilo ohms. So just to give you some of the an idea about some of the typical numbers you'll see for these resistances, etc. Of course, it depends on your actual device. Okay. So that was all the stuff we covered. So, the other thing is, we've been talking about bipolar transistor and forward active mode. And, the question is, and you're saying don't go into saturation. And what happens in saturation? Well, if you plot, I think I have one word for, at this level, I don't think we want to get too far into saturation. All I can just say is, when you're really, for the purposes of this class and probably most of what you guys will be designing, just don't do it. Like, usually bad things are going to happen when you go into saturation. Again, there were some devices I've seen here and there, some circuits that I've seen in 25 years plus that are in saturation, but they're a handful. So I think, basically what happens if you basically if VCE drops to below a certain value, this IC becomes a very strong function of VCE. So you basically are going to end up getting a non-working transistor once you go below a certain value. So, just in a nutshell, don't put your device into saturation. Nothing good is going to come out of it. Now you can go, we said we want the base collector to be, worst case at 0. But, you can be operating a little bit out here and still have a working device. It doesn't immediately roll off. So it turns out that your base collector could be as much as 400 millivolts, and it'll still be okay. So it can kind of push it. This collector can dip below the base, but the more you do it, you're taking away your operating margin. It means if something goes, your power supply gets modified, your resistor values aren't quite the resistor value you'd hoped for, this guy could go into saturation. So just normally I'd just say stay well away from this edge and keep your device in forward active. So I think that's the sum total of what I think I'd like to tell you guys about saturation. And then the last thing, we've got these models for saturation, etc. It's just, all sorts of bad stuff happens in saturation. So, okay. So the other thing I wanted to just make sure we just touched on, really, on just saturation and the PNP transistor. So we've been talking about the NPN bipolar transistor. And that's, you have the emitter, base, and collector. This is an N type, this is a P type, this is an N type. And we have, electrons go from the emitter to the base. to the collector, and some holes come from the base to the emitter. So these are the holes. These are electrons. Okay, so this is called the NPN bipolar transistor. But there is also another device called a PNP bipolar transistor. Which is a N-type material sandwiched between two P-type materials. So here for the PNP, the base is N, the emitter is P-doped, and the collector is also P-doped. And basically the way the current flows is you end up having holes, like a large number of holes, get dumped from the emitter into the base and get collected in the collector. And then your base current is a small number of electrons. So everything gets sort of inverted in a PNP as compared to an NPN. And so all our equations end up being similar. Oh, by the way, sort of being similar, except all the voltages and currents are inverted. Okay, so it's kind of like alternate universe here. And the drawing is a little different. So NPN, this is the schematic of an NPN transistor. The arrow always goes on the emitter, Okay, so this is emitter, base, collector. Now, for the PNP, the emitter is still on, the arrow is still on the emitter, but it points in rather than pointing out. Okay, so trying to imply a direction of the current. Sorry, this is the emitter. So the arrow is always on the emitter. And collector. Okay. So, and basically what you want to do to put this in forward active mode is you want the base to be below the emitter. Remember, this is a P-N junction, so you want the N of the base to be below the emitter. Okay, and then you want the collector to be further below the base to make this a reverse bias junction. So everything's flipped. So when we typically what we do on a NPN is something like this. You put a positive voltage on the base, so make the we're making the base higher than the emitter. Okay, and then we put another positive voltage on the collector that's even higher to make this junction reverse bias. We tend to do things in inverse in a PNP. So usually you see the emitter connected to a high voltage. Okay, and then you bring, put a battery and make the base a little smaller than the emitter to turn on that junction, the forward bias to junction. And then this guy basically goes here. Should go like this. See, yeah, I can go like. So this guy connects like that. Okay, so everything gets inverted. And then when we look at the large signal model, for NPN, for PNP, sorry, for PNP, I sub C is I sub S exponential of now it's V EB, not VBE, over VT. I sub B is I sub S over beta exponential of the EB over VT, and I sub E is beta plus 1 over beta I sub S exponential of the EB over, whoops, over VT. Okay, so this is how the values change. And the small signal models change correspondingly. I mean, they don't really change. You still have transconductance and R sub pi. You just connect it up in inverse. Okay, so let me just do a quick. You know, I depending on how far we get into chapter 5, we might not see PMPs again in the circuits. Depends. I mean, PMPs typically get used as ways to bias NPNs. When you don't, you can use resistors. There's some benefit to use transistors to bias up instead of resistors and things like that. So if you look at let me see if I can pull it up to give you guys an idea.
When you say this, like, do we just chain them together?
Can you say that again?
Do you just like chain them together when you're saying you're biasing the NPN with the PNP?
Let me show you, because I'm not sure what you mean by chain them together, but let me show you what it looks like. If I can do a screen share. This down. You guys see a schematic? No. What do you guys seeing? Are you still seeing my writing, or?
No, we only see your desktop.
Do you see something that says electronics hub?
Nope.
There was something that looked like a
Files.
static, but it left the screen.
Let me try it.
It says you're showing screen 3 right now.
That's such a complicated.
Now we can see it.
Now you see the schematic, electronics hub. You see it?
Yeah, we can see it now.
Okay, great. Thanks, guys. So here, I don't know if you can see my cursor, but for example, you see Q1 and Q2 are NPNs, but then Q8 and Q9 sitting on top are PNPs. So the way, you're just going to have to take my word for it, but the way Q8 and Q9 are configured, it makes Q8 look like a current source for Q1 for Q2 to bias up to basically set the current through Q1 and Q2. Okay, and same with like these Q12 and Q13. So like the signal, if you were thinking of the signal traveling through your op-amp, typically the signal is traveling through NPNs, and you're setting up your PNPs are kind of the ancillary circuits or adjunct circuits or peripheral circuits to make sure the NPNs are biased correctly. Okay, so They are very important devices, but like simple bipolar circuits, like the ones we'll see, probably take a look at in chapter 5, don't really, they still basically rely mostly on NPNs and resistors. So, as you guys progress, hopefully you'll be taking more of these microelectronics classes. You'll probably start seeing PNPs, like for example, in op amps, they're pretty common to see them. Anyway, I just wanted to, I think at this level, I think it's just important that you guys are aware that they exist, and they are like the NPN. You want to operate them in the forward active mode. You don't want to saturate them. The voltages are flipped. They tend to be much slower than NPNs. And their beta, which is the current between the gain of the current between the collector and the base, also tends to be lower. So they're just kind of not as good as NPNs for various reasons. Part of it has to do with like holes are slower than electrons. And just typically people are designing the process to be optimizing the NPNs, and the PNPs are sort of an adder. Anyway, so I think for the most part, just be kind of aware of them, that they exist. And then, if we do get a chance, if we do manage to get far enough along, we'll sort of visit them again. But okay, so let me stop this share. And then let me just do you guys a quick example of what the numbers on the PNP look like. You do a sample and how you would hook it up. Okay, back. Okay. So this is example 4.17 from the book. And so it's connected up a PNP. And as you saw in the schematic, typically PNPs are hooked up to the supplies. And NPNs are that's the way I would think of them. NPNs are mostly hooked up to grounds. But maybe that statement is just going to confuse you guys. But anyway, so this is the circuit, R sub C. Remember, this is the emitter now on a PNP. This is the collector. This is 2 volts in the example. And then this is 1.2 volts. Okay, so this is the base. So first thing we want to do, if you remember, the I sub C is VEB over VT. So now we're going to get the emitter. We want to figure out the emitter base junction, which is the voltage of the emitter minus the voltage of the base. VBE was the voltage of the base minus the voltage of the emitter. So it's 2 volts minus 1.2 volts is 0.8 volts. So still we got this 0.8 volts, but now the base is 0.8 volts below the emitter. And because it's a PNP, it turns on, it forward biases this junction. Okay, so I sub C then is just I sub S exponential of VEB over VT. And the example gave us I sub S as 2 times 10 to the minus 16, beta as 50, and it's sort of ignoring the early effect. The PNP, it has its own early effect, but we're ignoring it here. Here's a good, notice, remember, I don't know if you guys did the homework or not, looked at it, but a lot of time, the default beta in these problems is 100 for NPNs, and you can see that the beta on PNPs, this is implying it's not as good as the beta on NPNs, part of the problem with PNP. So anyway, this ends up being 4.61 milliamps, which isn't unusual. Sounds like a similar current. And then I sub B is just I sub C over beta. That ends up being 92 microamps. And I sub E is the sum total of those again. So that's ends up being 4.7 milliamps. Okay. And then V sub, we want to make sure that this is in forward active. So this is in forward active. We want to make sure this is in reverse active. So we want to figure out this voltage here. So just to verify it, so voltage at the collector is this current I sub C going through the collector, going through the resistor R sub C and above ground. It should be ground. Okay, so V sub C is just I sub C times R sub C plus 0. The 0 being this ground. Okay, so that's equal to 0.922 volts. Okay, and now again, because this is PNP, as long as this collector voltage is below the base, so the base is 1.2, this is 0.922, means this guy's reverse biased, and the transistor is in forward active. So let's run. Okay. So that's all I had to talk about NPNs and PNPs and bipolar transistors in general. And so, you know, this slide here, this slide 33 is kind of a nice summary of all the concepts. And you know, we just did the quiz, and sort of we're done with the chapter 4. So next Tuesday we're going to start with chapter 5 and start looking at some of the circuit designs in more detail. Any questions, guys?
Professor?
Yeah.
Is it possible to talk to you about the quiz after class?
Sure. And you can just log into the office hours.
Okay.
Okay. Any other questions, guys?
Yes, I've got a question.
Yeah.
So when it says find the operating points of the circuit and, you know, the practice problems, sometimes we would find VB or VBE, and sometimes we would find VCE. What's the reasoning behind that, one or the other?
Usually so if you're in forward active mode, what VBE and I sub C does is to find VBE is to find kind of G sub M and R sub pi. Okay, so if you figure out I'm sitting at this VBE1, it gives me a certain IC1, and from there I can find my small signal parameters. Usually, usually when we do V sub so far, whenever we do VCE, let's say there's no early effect for the sake of discussion. You basically just want to calculate VCE to make sure you're not in this bad place. Okay, so you want to verify, because a lot of times when you design a circuit and it doesn't work the way you expect it to, you've screwed something up and the VCE is too low and the device is entered in saturation. So usually what we've been doing, and I think a lot of the practice problems, are just calculating VCE to make sure it doesn't dip down too low for you to be in forward active mode. Now, if you have the early effect to contend with, then you also need to figure out VCE to figure out how this changes your I sub C compared to what you expect. Does that make sense?
Yep. Thank you.
Sure. Hey guys, any other questions? Okay, have a good
Thank you.
weekend.
Thank you.
Take care. Bye.